speaker, Ignacio Uriarte-Tuero from University of Toronto, who will talk about two-weight norm inequalities for single integrals in Rn. Please, Ignacio.
So thank you very much, Ilya, for the presentation, and also to Ilya, Damir, and Javad for the organization and the invitation. Organization of a great, not only week, but semester-long program. So, well, I'm going to talk about various pieces of work. They are all along the same program, no? Which is these two-weight norm inequalities for singular integrals in Rn. And there will be, various theorems with subsets of the co-authors displayed here. So Michel Alexis, Christos Grigoriadis, Michael Lacey, Mihalis Paparizos, Eric Sawyer, and Chan Jensen. So roughly speaking, well, the outline of the talk is that I will explain, it's all centered around the conjecture of Nazarov-Trail and Bolberg. So I will first explain a little bit about these two-weight norm inequalities, what they are, some easier classical cases, the Hardy-Littlewood maximal operator, then and also the Hilbert transform, what the easier cases of operators, that's what I mean. Then what are these A2 weights? What did Nazarov-Trail-Bolberg contribute to? And a certain counterexample related to one conjecture of theirs that also explains some ideas of the whole area. And then after that, then I'll explain some of the ingredients of the proof of the Nazarov-Trail-Bolberg conjecture for the Hilbert transform. So that's one very important case. And it's one of the few cases where everything is known. And then I'll basically explain two further developments. No? So one of them is local TOP theorems, which is a certain extension, very natural extension for T1 theorems. Then something about optimal cancellation, which is a development that will appear tomorrow in Archive. And if time permitting, there will be an application to Astalas conjecture. No? So basically, some of you may have seen some versions of, previous versions of this kind of talk, for this area. So some parts may be familiar, but some other parts, definitely the last one, which is what will appear in Archive tomorrow, is not, is new. Okay. So let's start with them. So the main problem we want to attack here is the two-weight problem, which is that we focus on p equals 2. Very little is known for other p's, and even p equals 2 is not fully understood. So anyway, we want to understand this norm inequality. So the pairs of weights for which you have, meaning locally finite Borel measures for which you have this inequality. Okay. And then these are important, for example, when, this kind of questions is important, for example, for Calderon-Sigmund operators, which I will essentially define later, and this is the focus of our talk. It will be most important when T is the Hilbert transform, because then it's equivalent to a certain perturbation question regarding some unitary operators, and then Rizor-Berlin transforms, or Cauchy, and then it's equivalent also to some perturbation theory for some other operators, and then it also appears, this kind or related questions appear in, for example, in the connectivity of manifold of corridor curves via quasi-conformal maps also, and that's an big open question in the quasi-conformal area. Or the proof of Astalas conjecture, there's a connection also, which I will explain time permitting, and there's other connections to the Saracen conjecture on the composition of boundedness of a product of two densely defined Teplitz operators, or the existence of this so-called Birkhoff-Wiener-Hopf factorization for a given function. No? So what are the model operators? No? The easiest operators we're going to be dealing with. Well, the first one is the Hardy-Littlewood maximal operator. So basically you take the supremum over averages of your function or the total variation of your measure, no? Over cubes with sides parallel to the coordinate axis. And the model Calderon-Sigmund operator, I won't give the technical definition, but they are essentially all of this type of operator. It's basically convolution with 1 over x, except that, of course, that is not integrable. So then you have to take principal value. And then it's a theorem that actually this makes sense, and it converges in LP and almost everywhere, and well, lots of nice things. No? So the idea is that you have a singularity that you are barely non-integrable. And then if you do principal value, etc., and you have like 1 over x or 1 over x to the n in Rn, appropriately, generalized, then you have these Calderon-Sigmund operators. No? The Hilbert transform, as we all know, it's well, it appears classical in complex analysis. For example, if you take a nice function, whatever nice means, on the real line, you take the Poisson extension, take the harmonic conjugate, take the boundary values. That's the Hilbert transform of the original function you started with. So that's a connection with complex analysis in this talk. Anyway, okay, so let's focus first on these two operators, these two classical operators. So the next thing I want to mention, another ingredient in this soap opera, let's say, another main character is the A2 weights. So classically, a weight is an L1 locally non-negative function, and will denote the measure of a set by any of these three notations. No? Then we say that a weight is an A2 if and only if the average Lebesgue average, so with respect to Lebesgue measure of the weight times there's the same Lebesgue average of 1 over the weight, the reciprocal of the weight. This is uniformly bounded over all cubes with sides parallel to the axis. Okay. So if you put together classical theorems of Koefman, Pfefferman, Handmack, and Hauptmann-Witten, you have the following very nice characterization. So if you have the Hardy-Littlewood maximal operator, then the operator is bounded from L2 of the weight to L2 of the weight if and only if the weight is an A2. Okay. And this equivalence is essentially true also for any decent Calderon-Sigmund operator. So decent means that it's non-degenerate. So for example, that not only you decay at most like 1 over x, as in the case of the Hilbert transform, or 1 over x to the n, but also you decay at least like that up to a constant function. No? That's so-called elliptic on every direction. And then for those cases, for those operators, you also have this equivalence, but the implication from the boundedness of the operator to A2 assumes that every ball is positively charged by your measure. Fine. This is a classical theorem, and it's a wonderful theorem in that, well, maybe I should have said before, for the Lebesgue measure, this is clear. Of course, Lebesgue measure is an A2 weight, so that's fine. Then when you wonder about one weight, you have a very simple characterization because A2 is a very simple condition to check, and it's necessary and sufficient. So this is kind of a dream theorem. The problem is, well, it's going to get more complicated, of course. So, okay, one more comment before I explain the further complication. Where do these AP or A2 weights appear? Well, there is something called AP, which is basically a similar expression, but with some p in it. Here it's to the 1 over p minus 1, this kind of reciprocal. And then there's a corresponding theorem for LP weights about the boundedness of the Hilbert, maximal Hardy-Littlewood maximal operator or Calderon-Sigmund operators. And these AP weights also appear as Jacobians of quasi-conformal maps. They also appear as the Radon-Nikodym derivative for the density with respect to surface measure of the solution of the Dirichlet problem on bounded local ellipses domains. Okay, let's say, yeah, okay, like this one. And they appear in, other circumstances, but these are a few places where they are classically encountered. No? So once you understand the problem of one weight, then it's natural to wonder about the two-weight problem. So the naive formulation of the two-weight problem would be this first line in this display. There's a standard trick, which is to write H as F sigma. Sigma is 1 over V, and then this inequality becomes this. So instead of looking at the two-weight problem as in this first display, we're going to look at it as in this display, and there are several reasons for it. So for doing so, the first one is that, if this two-weight problem is to be solved or makes sense, there's I mean, it should also make sense for measures, in particular for singular measures. So you could have a V here that's a singular measure. T is defined as usually as integration with respect to Lebesgue. H may be, for example, measurable with respect to the singular measure, then TH is not clear what it is. Whereas here you have F sigma, then it's clear or clearer what it is. Also, along the same lines, V is a singular measure and H vanishes on the support of the singular measure, but not as a function in Rn. Typically, this is non-zero, this is zero. This wouldn't happen here. You would get zero in both sides. No? So if you want to look at measures, as opposed to just L1 local functions, this second formulation makes much better sense. Another reason is that the dualization here, in this sense, is very simple, very convenient, because the dual of this inequality, you just swap the measure sigma and omega. And there's another reason, which is that, I mean, it's hinted in this last line, which basically says that, well, we will look for a characterization of this inequality, as we said at the beginning. No? The previous characterization, meaning the one-weight characterization for AP, or A2 in this case, as in A2 weights, is wonderful because it's simple and it's necessary and sufficient. But the moment you go to the two-weight problem, this kind of characterization or a condition, the A2 condition, with two weights, so it's the same condition as here, but instead of putting 1 over omega, you put sigma. Turns out to be necessary, but not sufficient. And then there's a huge literature to try to improve that condition to get something necessary and sufficient. Well, that literature, I mean, it's extremely good, very important. The nice thing is the conditions are simple to check because they are slightly strengthened versions of the A2 condition. The bad thing is that there's very sharp theorems in that literature, but they are not necessary and sufficient. So, I mean, of course, you should first check those conditions, which are sufficient and very sharp. But if at some point your life depends on knowing whether the inequality is really true and those conditions are not satisfied, then you need a plan B. Okay, I'm going to talk about the plan B. So it's conditions that are going to be necessary and sufficient. And for these kind of conditions that I will explain in a moment, this is the correct formulation. I'll explain in a moment which kind of conditions I'm talking about this. Okay. So, as I said, this is the two-weight A2 condition. So it's the same as before. Before it was omega and here 1 over omega, now it's sigma, okay? And the theorem, the analogous theorem to this theorem here in the two-weight world is the following. On the one hand, the maximal operator sends L2 to L2 weak, the weaker version, if and only if the weight pair is A2. This is the same, it essentially has the same proof, same idea as the one-weight theorem. No? And the one-weight theorem, actually, you also get L2 to L2 weak. But when you have a one-weight, which is in A2, it self-improves by something called the reverse Helder inequality. So then you can get a little bit better behavior, and that allows you to conclude the strong inequality. This is false in two weights. In the two-weight world, there are cases where the maximal operator is bounded in the weak sense, but not in the strong sense. And then one wonders, okay, what's the corresponding characterization for the norm inequality? So Eric Sawyer in 1982 proved the following theorem, which is that you have the characterization for the norm inequality if and only if the norm inequality holds with a uniform constant for a subclass of all the functions you want to consider. So instead of all L2 functions, characteristic functions of cubes. Moreover, in this case, you only need to integrate, I mean, this should be an integral over Rn. Well, it's enough, I mean, actually it's necessary and sufficient to check the integral over Q. And these are going to be what we call T of 1 type conditions. So again, the good thing, I mean, this is kind of a plan B, because the A2 condition is very easy to check, but it turns out that, I mean, it's not sufficient. strengthened conditions of A2 are going to be sufficient, but then they are not necessary or not necessarily sufficient. And then if you really need a necessary and sufficient condition, this is the kind of condition we are going to be looking at. The disadvantage is that this condition is much harder to check. Some people say it's impossible. Well, I strongly disagree with that assessment, but I do agree it's harder to check. And I will give an example later about a case in which we could check it and prove a theorem, in particular Astalas conjecture, I mean a certain key inequality in Astalas conjecture. So, okay, so as I said, we are going to look for this kind of conditions and this kind of characterizations of the strong norm inequality. And we already saw in the simplest operator, or one of the simplest operators, the maximal operator, that this is stronger strictly than the weak type characterization, the A2. So now let's look at the easiest Calderon-Sigmund operator, continuous Calderon-Sigmund operator, which is going to be the Hilbert transform. So we want to characterize the norm inequality again. So it's this one again here. So, of course, there are two obvious necessary conditions, namely the testing conditions, which is that the inequality for the Hilbert transform holds uniformly over all intervals with a certain constant. Okay, so this is the same as the norm inequality, but just plugging in the function, characteristic function of I. And the dual, as I said, as I explained before, the dual is you just swap sigma and omega. Okay, so these are obviously necessary. The first one for the maximal function was already also sufficient. Here we will need a little bit more. So there's another testing condition, you can think of it as a testing condition, which is that instead of testing characteristic functions of intervals, you can test this function. And technically you test cutoffs, appropriate cutoffs, then you take limits, blah, blah, blah. But essentially you test this function. And then you obtain from the norm inequality that the following condition holds. The following condition is the fattened A2 condition. So the standard A2 condition in two ways is, well, it's here. Okay, one moment. Okay, this one here, which we know is necessary. In this case, for example, the Hilbert transform, even more is necessary. So this is like A2, but instead of having the characteristic function of a weight here, of an interval, and then you take the Lebesgue average, you take the characteristic function and you add to it a Poisson tail, which is this one here. So of course, this is a larger number. So this supremum being finite is even stronger. So it turns out that these three conditions are necessary. And the conjecture, by one big conjecture by Nazarov-Trail-Goldberg at the time, was that these three conditions would be sufficient. Okay. So, and Nazarov-Trail-Goldberg, in trying to prove this conjecture, they introduced something called pivotal condition, which basically says, it's used to control some off-diagonal terms, which basically says that if you have an interval I0, you decompose it arbitrarily into arbitrarily disjoint subintervals, which are a partition, let's say, and then you look at this kind of expression on the left, and you want it to be bounded by some constant. P is the best constant, the same way as before H and H star or A2 were the best constants in these inequalities, times the sigma measure of I0. So, couple comments. First of all, these kind of things, these kind of expressions on the left, they are sort of measuring in some way the oscillation of certain, of the singular integral you want, or it's an upper bound for the oscillation of the singular integral on certain these intervals I0 whenever the measure is supported away from, sorry, I said I0, I meant IR, when the measure is supported away from this IR within I0. No? So this is a different kind, a certain kind of sum of average oscillation of the singular integral, if you want to call it like that. The second thing is that one kind of, numerology, if you want, in this area, is that here you have an omega, here you have twice a sigma. So each time you have an omega and a sigma, they should morally cancel, as in the A2, so you should be left with one sigma. So that's kind of the homogeneity rule here. No? And of course, as usual, if you impose a condition, you impose the dual one, just interchange the two measures, and then you have a best constant, which is P star. Okay. Okay, so the theorem by Nazarov, Trial, and Bolberg, and I'll explain in a moment why it has two dates, is that if you assume these pivotal conditions that I just explained, then the two-way norm inequality holds if and only if testing, dual testing, and A2 hold. And they conjectured at the time, or stated, if you want, that these pivotal conditions might be also necessary for the two-way bound for the Hilbert transform. No? This smaller conjecture was later disproved by Lacey, Sawyer, and myself. Okay, so if the measures sigma and omega are doubling, then the pivotal condition is true, and then, well, this is a very strong theorem. But then, of course, the enemy is non-doubling measures, because then you lose control in stopping cubes. The standard Calderon-Sigmund decomposition, or one of the standard ones, is that, okay, you start with some cube, you have a function, let's say positive, or you take the absolute value of the function, and then you start looking at the average of the function, let's say on the starting cube, and you go down until the average of your absolute value blows up by a certain constant factor, like 10. Then you stop, and so on. No? So with Lebesgue measure or with doubling measures, the first time you stop, because you didn't stop in the parent, you have a certain control from above of the average. With non-doubling measures, you lose that control. And that's a big technical enemy in this area. Okay. This theorem by Nazarov, Trial, and Bolberg was proved in 2000, posted in some, well, preprint collection in Barcelona in the CRM in 2000. And then, well, it was lost by at least one of the authors. And, well, and when that author recovered a copy of that theorem, they posted it in 2014. You can see that same comment in Archive, no? But it's a great theorem. Okay. And it really started, I mean, it was really a strong milestone in this area. So let me give you I mentioned here that the pivotal conditions might be necessary, as conjectured by Nazarov, Trial, and Bolberg, but then they were proved not to be necessary. So let me give you the example that proves the lack of necessity of that. And it also has a certain moral for this whole area, this problem. Omega is going to be the Cantor set measure. So you take the usual 1/3 Cantor set, you assign equal weight to each one of the intervals in the construction at every level, you take a weak star limit, that's your Cantor measure. Fine. The sigma measure is going to be a sum of deltas. And the deltas are going to be placed close to the center of the gaps. The gaps are here colored in blue. What's the weight of each delta? Well, for example, look here in I21. Pretend that nothing exists except the gap and the two neighboring intervals. And then you would like to say, well, if it's going to satisfy A2, it should satisfy it at least relative to this, to the triple of this gap. No? So then you know what's the measure of the triple of this gap, because it's the union of these two gray intervals. You impose the A2 condition as if there was no other delta measure with, let's say, equal to 1. That gives you the mass for the delta function you're going to place here. And if you impose that, those masses at all the gaps, more or less close to the center, provided you are reasonably close to the center, this per omega Cantor measure sigma, this guy, is going to satisfy A2. Okay. So now the natural place, or the first natural place to put these masses is going to be the centers. If you do that, as I said before, you satisfy the A2 condition. You also satisfy the forward testing condition, but fail the backwards one. So the forward one is this one, sigma inside, omega outside. Backwards is the opposite one. Okay. And this already shows, well, first of all, it shows that the norm inequality doesn't hold in this case, because both testing conditions are necessary. It also shows that A2 and testing conditions are independent, in the sense that you could satisfy one of the A2 and one of the testing, but not the other. There was a similar example in this respect previous to this one, more involved, due to Nazarov, Bolberg, and another one, Nikolsky and Trial. Okay. So now let's move slightly the position of the delta masses. So here in the central interval, it's still in the center, but otherwise we put it in the zeros of h omega. So, I mean, h omega on the gaps is going to go from minus infinity to plus infinity. It's going to have an unique zero. And the unique zero is going to be close to the center with uniform bounds relative to the size of the interval. So scale invariant uniform bounds. This pair of weights does satisfy the two-weight norm inequality. I haven't told you why, but it does. So it does satisfy A2 and the two testing conditions, but it does not satisfy the dual pivotal condition. So this shows that the pivotal conditions are not necessary. And notice I mentioned that we are placing the weights very close to the center. So a small perturbation of the problem changes dramatically the behavior. Here we satisfy the norm inequality, here we don't. So this problem is extremely sensitive to perturbations, and forget about any perturbation method. Okay. So, okay. The next thing is I'm going to explain a little bit about some of the ingredients of the proof in the case of the Hilbert transform. So the first main theorem is a two-part paper. The first part is Lacey, Sawyerson, and myself. The second part is just Michael Lacey, in which we proved the Hilbert transform, I mean, the Natasarov-Trail-Goldberg conjecture for the Hilbert transform for locally finite Borel positive measures, assuming the measures have no point masses in common. Okay, this is just a technical hypothesis that, well, we wanted to avoid a certain technical issue, and we have otherwise no side conditions. Okay. Then Hitonen later removed this technical condition, the point masses in common. The way he did it is the following. So if you have a point mass, I mean a 1 point mass in common, if you go to the A2 condition, which is, for example, here, here. Well, assume you have a point mass in common and take the cubes that shrink towards the point mass. Both of these integrals are going to be positive, like 1, but because of the 1 over q, you're going to blow up. So the A2 condition blows up if you have a point mass in common. What Hitonen did, and remember also, sorry, that you have a similar condition for the Hilbert transform with tails. So what Hitonen did is he ran the same proof. I mean, of course, running the same proof means 40 pages plus lots of technical issues. So I'm simplifying here, but anyway. But the main idea is that he ran the same proof as our theorem here, but with the A2 condition with holes. This means in the sigma world, you still have the characteristic function. In the omega world, you have the Poisson tail, but away from I, in the complement of I. This means that you don't see common point masses, but you essentially have the two, I mean, the same kind of A2 condition type thing. And of course, the dual one as well, of course, the dual A2 condition with holes. You run the whole proof, it works. And that was what Hitonen did in his paper. So the Hilbert transform is completely understood. What are some of the ingredients, or maybe you could argue maybe one of the main ingredients in the improvement over Nassarov-Trail-Goldberg's scheme of proof? Well, you could argue it's an idea from, I don't know if you want to call it mathematical physics or probability. Basically, you take the variance of the random variable x in the interval I and you normalize it. This is this energy guy. We call it the energy. So the variance, of course, measures how spread a random variable is. Because we have normalized, in this case, to the interval I, it's at most 1. But if the random variable, I mean, in the measure, it's extremely concentrated, like 1 point, then this is going to be 0. Okay. And this is going to improve the smoothness of the kernel estimates. So in order to show that, I'll show a short calculation, which is a toy model, but contains the basic idea of how this energy condition fits into the proof to improve the Nassarov-Trail-Goldberg theorem. You define the average like this, the expectation, I mean, with this notation, this math bold E. we consider the so-called energy condition, which is the same condition as the pivotal condition, except that we're including here this energy factor. Since this energy factor is at most 1, this is a weaker condition, okay? But otherwise it's the same. You have your I0, you have your sub-decomposition or partition of I0 into IRs, you still measure the oscillation or an upper bound, and you require that still the same homogeneity because E is dimensionless. So it's clear from here, I hope. Yeah, the expectations already, cancel the measure. So again, 1 omega, 2 sigmas, so you get 1 sigma here. You require this and the dual condition. And well, this is the so-called energy condition. So this turns out to be necessary for the Hilbert transform, whereas pivotal is not necessary for the Hilbert transform. How do we use it? Well, if you go to the standard computation that we all do when we wake up in the morning for singular integrals, let's say we are doing with the Hilbert transform. We're dealing with the Hilbert transform, as is the case here. If you remember, you do the good and bad decomposition, and the bad function is a sum of bj's which have average 0 and supported on ij's. So after the standard considerations, matters are reduced to this integral. So the contribution of Hilbert transform of bj outside twice of ij. And then, well, as we all know, the great idea of Calderon and Zygmunt was to subtract 0, but a very clever 0. So they subtracted the kernel evaluated at some particular point, for example, the central of the interval, but need not be, which you can do because the integral of bj is 0. And then because we are sufficiently away from ij, namely we're away from 2ij, then this 1 over x minus 1 over x prime decay type thing behaves like a square decay here, and then we win. Okay, and this is, kind of the thrust, or one of the thrusts for the whole Calderon-Zygmunt machinery. So now we repeat the same thing, but with weights. So I'm going to repeat the same calculation, but the weights are in blue. Now we have the bad guy, the bad guys with respect to omega, and then we repeat the same calculation, but here, instead of choosing the center, so x prime being the center, it's more efficient to let omega choose what the point should be by the expectation. Why? For example, because if omega happens to be a delta mass, which need not be at the center of the interval, and you let omega choose the point in this way, then this whole thing is 0. So the choice of the x prime now matters. Once you do that, then you basically run the same thing, but this already points to the fact that under certain circumstances, you have a way better estimate. So, okay, so you put the absolute values inside because now we have already taken advantage of cancellation, and we do Cauchy-Schwarz, and here you have this guy is essentially one of the things that we have on the left for the energy condition. It's essentially except for a square. No? So basically, one moment, it's this thing, the square root of this guy. Okay. So in this way, as I said, we're measuring the oscillation. You insert this into the Nazarov-Trail-Goldberg Hughes machine, into the scheme, and that's how we proved the two-way theorem for the Hilbert transform. Because, as I said, in the case of the Hilbert transform, the energy is necessary. So this is, let's say, one of the 3 stories I wanted to tell, no? On this topic, no? And this kind of finishes the understanding of the Hilbert transform. What do we know after the Hilbert transform? Well, for T1 theorems, this is what's known until today, or let's say until today. Okay. So let me summarize or explain this diagram. Huh? N is the norm inequality. We know that if the norm inequality holds, then the 2 testing conditions, for Hilbert I call them H and H star, now it's T and T star, is this fracture T, okay, are necessary. We also know A2, and even A2 with tails also is necessary. provided the operator is not degenerate, as the Hilbert transform, but usually necessary. And there's also another condition, the weak boundedness property, which, as the name suggests, is pretty weak, and we're going to get rid of it soon, so don't worry about the definition. Okay, but it's also necessary. Okay, we would like, and that's the ideal world, to say testing plus A2 implies the norm inequality. Well, if you add pivotal conditions, like here, these pivotal conditions imply the energy conditions. We already saw that because the energy conditions is the same thing, but with a smaller, a weaker condition. We add this factor that's smaller than 1. And then Nasaroff-Taylor-Goldberg proved that testing A2 and pivotal, which implies energy, implies the norm inequality. What we did, as I said before, in the Cantor set example, we proved that the norm inequality does not imply the pivotal conditions. However, if you assume the energy conditions which are necessary for the Hilbert transform, this is this dotted arrow, in the case of the Hilbert transform, testing an A2 with tails imply the energy conditions. So the general theorem is testing an A2 with the energy conditions implies the norm inequality. That's a kind of big theorem, big, if only because the paper is like 100 pages long. So this was our theorem. Okay, then there are a few technical improvements. So for example, this WBP condition is not needed. Definitely for uniformly full dimensional measures, that's a theorem of Lacy and Wick, and in the general case, it's a theorem of Sawyerson and myself. Fine. Then we still try to prove the if and only if, so we want to know what happens with these energy conditions. They are necessary for the Hilbert transform, so maybe they are necessary in general. Well, we start checking some special cases. For example, if one measure is supported on a curve, or something called uniformly full dimensional measures. This is a theorem of Lacy-Wick, or a generalization of that, which is K-dispersed, whatever that is. But these guys, for example, include doubling measures. If you have this, you satisfy something called energy reversal, which again, don't worry too much about it. It's going to disappear in a moment. And this energy reversal implies energy. The problem is these are very special conditions. Okay, does this energy reversal follow in general? It does not. We have a counterexample. Okay, well, maybe the energy conditions follow in general. They do not. There are two counterexamples. One by Eric himself, another one by Eric, Chen-Jen, and myself. So this is basically the situation up to yesterday, or up to today. And in a sense, we are to some extent stuck, meaning these energy conditions are very nice. They hold for the Hilbert transform. They hold for a few other special cases. They don't hold in general. And the only way to prove the norm inequality that's known goes through the energy conditions. Or again, until today. Okay. So even for the proof that the energy conditions are not necessary, that's proven by checking the energy conditions. Then for a certain configuration of measures and operator, then we perturb slightly the measures so that the norm inequality still holds, but now for this perturbation, the energy condition do not hold. The energy conditions do not hold. So no matter what, you basically always have to go through energy. Okay. And this, as I said, was the state of the art until today or yesterday. Okay. So now there are two other stories I want to tell. One of them is a generalization of T of 1 theorems, which is the local T of B theorems. And the other one is the development in the last few hours. So local T of B theorems. Let me explain briefly what they are. The idea for a T of 1 theorem is that you test the integral T alpha, think alpha equals 0. Alpha is a parameter for fractional integrals over the function 1 over Q. Okay. And then you have here the measure of Q. So that's what happened, for example, here. No moment. Yeah, here. Okay. It's nice, but for whatever problem you have at hand, sometimes it's more convenient to test over other functions. A classical example of this is the proof of the boundedness of the Cauchy transform over Lipschitz graphs. This is a one-weight problem, and you have a solution with T of 1, which is long and involved, but it works. But if instead of 1, you could choose another function called B or BQ, no? Which may depend on the cube, but it's reasonably close to 1 in a sense I will explain in a moment. Then you have half a page proof, very simple proof. Of course, the difficulty is improving that theorem, no? That allows you to put a B instead of a 1. So what kind of B's do we allow? Well, first of all, they are going to depend on the cube, and they are supported on the cube. But they are close to 1 in the following sense. On the one hand, they are not too degenerate, so the average is far away from 0. On the other hand, far away by uniform constant, which could be very small, but anyway. On the other hand, they are not too unbounded. Okay, so you either have L infinity norm or sometimes LP norm. Okay, so not too unbounded, at least on average. Now, in our case, the broader family of such functions would be that these BQs are allowed to be in L2. We are going to take here P bigger than or equal to 2. L2 is the broadest one. P strictly bigger than 2 is a little bit more narrow in terms of the choice of, possible choices of these test functions. But, well, they are pretty broad. You have much more flexibility than with characteristic functions of cubes, no? And of course, you include the testing conditions, the testing and the dual testing. So if you assume that, and we call this a family of P weakly mu accretive family of functions, okay, mouthful, but okay, these B functions, these testing functions, then we have the following theorem proved by Christos Grigoriadis, Michalis Paparizos, Eric Sawyer, Chan Jensen, and myself last year, which is that if you have locally finite positive Borel measures, you have a standard fractional elliptic and gradient elliptic singular integral operator. Elliptic is non-degenerate in any direction. Gradient elliptic is something which is like that, but more uniform. Okay, but it's a standard operators like Berling, Cauchy, and Hilbert, or the vector of Riesz transform satisfy this. No? Then we have P strictly bigger than 2. That's a slight limitation. We would like P equals 2, but still we have lots of flexibility of these testing functions, BQ. And then we have that the norm inequality holds, assuming we have the testing conditions. This we know are necessary. The A2 conditions, I didn't define all these A2. I defined this one with tails, but they didn't define the punctured one, but it's along the same family, okay? And the energy conditions. And moreover, of course, if we have the Hilbert transform, we already know the energy conditions are necessary. So for R1, we actually get comparability here. The case of R1, the real line was proven before in a previous paper just by Eric, Changen, and myself. Okay. So this theorem, just to compare it to other previous theorems and to, and locate it within the literature. Well, let's compare to, let's apply it to the one-weight case. If you have a one-weight case, then the classical A2 condition becomes what's called nowadays upper doubling or polynomial growth measures. In this case, assuming you have this, the A2 conditions and the energy conditions are automatically satisfied. So if you plug in, this situation for the previous theorem here, this one, we recover exactly a theorem of Lacy and Martikainen, except for, well, then it's not exact, of course. We assume P bigger than 2. They assume you can take P equals 2, but of course, 2 weight is much harder. Okay. So, okay, this is a pretty general local TOP theorem. What are the ideas of the proof or the difficulties from the one-dimensional case? In one dimension, we use, to prove the corresponding local TOP theorem, we make a fundamental use of Hittonen's characterization of the restricted bilinear inequality, which is basically that you have almost Hilbert of F, except that you have absolute value, so it's bigger. Against G, they are supported on disjoint sets that are intervals, interval and its complement. And then this guy is bounded with some constant, and the best constant is basically A2, comparable to A2. You try to run this in higher dimensions and it's false. There's a counterexample proved by Michalis and Christos. So we had to substitute this with a certain use of probabilistic techniques, which it's a pretty involved technical tool called the surgery invented by Nazarov, Treit, and Bolberg, no? To handle the nearby term. The next difficulty is that, this characterization of the restricted bilinear inequality by Hitonen also helps to use the so-called full testing condition. The full testing condition, I haven't defined it, but it's basically the following. Let's look at T of B or T of 1. In T of B or T of 1, you only integrate over Q. That's testing. If you integrate over Rn, that's full testing, which of course is a stronger condition. Same right-hand side. Okay. So in one dimension, full testing is available. This allows to prove the so-called PLBP, pointwise lower bound property, namely that without loss of generality, we can modify the testing functions BQ to assume that they are bounded below, strictly bounded below pointwise. This is not true in higher dimensions, but it's true in most places, or essentially, due to a certain Carlson condition satisfied by the places where this fails, kind of. Okay. So that's how we circumvent that. And then we also did something called indented coronas, okay, to be able to, to get the higher dimensional case. So this, basically, I think this follows, yes, this takes care of the second story I wanted to tell, that is the local TOP theorem. And this is the state of the art for local TB in this world, in this two-weight world. Okay. The third story is the development in the last few hours. Well, admittedly, the publication is in the last few hours, or will appear tomorrow in arXiv. The theorem took a little bit more than the last few hours to develop, of course, which is the so-called optimal cancellation conditions. So let's digress for a moment to explain this problem, which is very related, and then we'll converge immediately to this kind of, to the rest of the talk, no? With these T of 1 theorems. So again, if you go to your basic, the first lecture in singular integrals or whatever that you attended, or first few lectures, you remember there is an old problem, which is, what are the optimal cancellation conditions for a singular integral operator with associated kernel K, so that it's bounded in L2 with respect to Lebesgue. We are assuming the kernel is smooth. Okay, we don't get into the rough kernel story. Okay, so the first very easy condition, or reasonably easy nowadays, is that K is an odd, smooth, homogeneous convolution kernel. This is very old, from Calderon-Sigmund, pretty much. If you still stay with convolution kernels that are homogeneous, once you have the odd smooth guys, you can do even smooth because of the method of rotations, provided the integral on the unit sphere is 0. Fine. Next thing, you say, maybe instead of the integral on the unit sphere being 0, one can prove, and you can check, for example, in this, this is in the classical book of Stein singular integrals, that if you have a convolution kernel, so we're still with convolution, smooth, but satisfies that the integral is 0 over spherical cells uniformly, then this cancellation condition, I think I made it wrong. Well, anyway, you just need it. Well, anyway, and you have a gradient condition, then it holds. No, I think this is just uniformly bounded. This is a typo. It's enough to have it uniformly bounded, independent of epsilon and n. Okay. In all these cases, these are cancellation conditions. They are sufficient to prove that the operator T is L2 bounded, just because the Fourier transform of the kernel K hat is going to be bounded. And this works via the Fourier transform because the kernel is a convolution kernel. Okay, how about non-convolution kernels? You can then pretty much forget about the Fourier transform. Well, then there's a lot of literature that basically look at conditions of this form, this kind of more general cancellation conditions. Okay, and then but they are all sufficient, which is fine, but okay, not necessarily insufficient. The end of the story was given by a theorem in Stein's fat book, the harmonic analysis book, which basically says that this condition up here is necessary and sufficient for cancellation. And it's Stein presents this as a, let's say, pretty much 4-page consequence, argument, which derives this condition as a rather direct consequence of the celebrated David-Journet T((1) theorem, which says that T is bounded on L2 of Lebesgue if and only if you have the two testing conditions for all cubes. So now we converge again to the previous part of the talk, okay? Namely, testing, T((1) theorem. So this in Lebesgue, T((1) is equivalent to optimal cancellation conditions to understand when the operator is L2 bounded. Because once it's L2 bounded, of course, you can run all the calculation machinery to have LP bounds, etc. Okay. Okay, so this is Lebesgue, and I'll be done in a minute or 2 minutes. So how about one weight? Well, let's say you have one A2 weight. Well, then you can reduce to Lebesgue. How? First of all, the classical, one easy case is if you are bounded on unweighted L2, then by Kaufman-Pfefferman, we know that T is bounded on L2W using that the weight is in A2. But the converse is also true. Assume T is L2 bounded on one single A2 weight, not all of them. Okay. Then by duality is bounded also on L2 of the dual weight, 1 over omega. Then by interpolation, the Stein-Weiss theorem on interpolation for change of measures, you get that T is bounded on unweighted L2. So the Lebesgue measure. So the one weight problem for weights in A2 is just reduced to the case of Lebesgue, which was solved before. Okay. Okay, how about two weights? Well, the analog, the testing conditions, we know what they are. The analog of Stein's cancellation condition is the same, except that here you have a sigma, here you have an omega. And, well, you have pretty much the same condition and the dual, because now you have to interchange the measures. There's a slight, well, sorry, when you change the measures, you also change of course, the kernel for the dual kernel, no? There's a slight technical issue. Stein ran all his whole T((1), his theorem, for his theorem, he ran the T((1) proof, basically with Littlewood-Paley theory. This gave him balls, and then he got the cancellation condition in terms of balls. We use wavelets related to cubes. So then we have to take these balls as cubes, so basically the L infinity norm. But otherwise it's the same. So where is this? The main theorem is the following. Assume you have locally finite positive doubling Borel measures. We have to restrict to doubling. The rest is basically assume you have your favorite alpha fractional singular integral operator, smooth kernel, and assume you're strongly elliptic. Again, this is a non-degeneracy condition. We can do slightly better, but let's say, and this covers all the classical cases, Cauchy, Berling, Hilbert, etc., vector Riesz transforms. So then the following are equivalent. Either you have L2 bounds, in the sense of uniform boundedness smooth truncations. The testing constants are finite, so this is necessary and sufficient, no side condition. It is a characterization, or the cancellation constants. So this is saying these are the optimal cancellation conditions, because again, it's if and only if, okay? And moreover, the norm inequality is equivalent to testing plus A2 with tails, or A2 without tails and full testing. Remember, full testing, it's kind of almost fits bottom of the slide, is integral over the whole of Rn. Okay, that this is finite, and then the dual thing with changing the constants. Just a few words or comments, and yeah. First of all, the inequalities. The upper inequalities hold always, whether it's meaning no ellipticity assumptions. We do need doubling. Second thing, sometimes the operator is defined in terms of a kernel, and that the operator on the function is has this integral representation away from the support. This is also equivalent. I didn't add it before not to clutter more this slide. And also there's a technical condition when alpha equals 0, we have to assume that there is an operator T0 which is bounded on a weighted L2. Ideas of the proof, this is the only slide about the proof. The general scheme of the proof is the same as before, Nazarov-Trail-Bolberg, or Lacey, Sawyer, Sen, and myself. No? The energy conditions, as I said before, are necessary only for the Hilbert transform. So we have to find a substitute. There is a substitute which is a weaker version of the pivotal condition, in which the pivotal condition you have decay like 1 over x squared. Here you have decay like 1 over kappa. But this follows from doubling. This is a strong use of the doubling condition. But if you have doubling, you will have that for a sufficiently high kappa. In order to use it, you need to use higher order Taylor expansions of the kernel. That's fine. We have assumed smooth kernels, and the so-called weighted Alpert wavelets. These are like hard wavelets for weighted spaces, but hard only have average 0. These have higher vanishing moments. That same story. Now, the methods that are used in this scheme require Calderon-Sigmund stopping times and coronas, which require L-infinity estimates for these weighted Alpert wavelets. Well, in order to get these L-infinity estimates, you need doubling. This happens if and only if the measures are doubling. So this is another strong use of doubling, the doubling hypothesis. Then you run the whole proof. You have the paraproduct neighbor stopping decomposition, which is, okay, whatever it is. But before, we had to take out a constant, a polynomial of degree 0, out from the singular integral. Here, because of the Alpert wavelets, we have to take out a polynomial. This introduces a commutator term. This is the hardest part of the proof. It's a completely new ingredient and technically pretty hard. And I won't have the time to discuss the application on quasi-conformal maps, but basically there's a tier 1 theorem at some point that helps to prove, the conjecture. And this is the list of references, in which I'm not including the one that will appear tomorrow in the archive because we don't have a reference yet. Thank you very much.
Thank you, Ignacio. Let's thank Ignacio for a wonderful talk. Questions, comments, suggestions? Well, if there are no questions, let's thank Ignacio again. And that concludes our today's session. We'll see everybody here tomorrow at 11 Toronto time, Toronto virtual time, at the Sergei Trails colloquium. See you tomorrow. Bye-bye.